Hello, chemistry students. All right, so this is our first pre-recorded lecture video where we're going to be taking a look at the tail end of Module 1, just to wrap that up. And today we're going to be taking a look at the bonding that occurs within a variety of different substances. Okay, and so we're going to be looking at ionic bonds, covalent bonds, looking at metallic bonds. All right, we're going to use this to eventually go into talking about molecules and so forth in later videos. Okay, so just pointing out this just here, we are looking at the bonding, the final inquiry question of Module 1, and we're going to be looking at what actually holds the atoms of compounds and elements that form elements together, okay, and keeps them held together in materials. Okay, so just getting ourselves started just here, I'm going to remind you of the model we're using for a chemical reaction. And in this model, what we have happen is our reactants, our starting materials, the particles that make up those materials, they need to collide together successfully. The bonds that hold them together has to break and rearrange to form the new bonds in the product material. All right, so the bonds that are holding together materials, super important, people. Now, I'll get you to recall from the periodic table trends you've been looking at over the course of the holidays, we have electronegativity. Now, this is a measure of how much an atom or an element, how much an element wants to grab a hold of additional electrons to fill its valence shell. All right, now the Pauling scale is what's commonly used, and on that scale, all right, fluorine is assigned as being the most electronegative element. And so what that means, let me just turn annotation on just here, is that basically, so we have fluorine just here, as we move across the periodic table and as we move up, all right, we get more electronegative, okay? Essentially, what that means is if it's near fluorine or it's fluorine itself, it's going to want to take electrons. If it's away from fluorine, all right, it's usually wants to give away its electrons. And so if we take a look at visually different way of representing this, all right, this is a representation of the periodic table, and the size of the green circle is a representation of the electronegativity on the Pauling scale. All right, so you can actually see just here that fluorine, right there where the X is, okay, that is that's the biggest circle on the periodic table. Okay, and so as we move across from left to right, our electronegativity increases, and as we move up towards fluorine, our electronegativity increases. And so elements that are sitting in that region of highly electronegative, they want to take electrons, and elements that are sitting over here, they want to give away their electrons, okay? And that's still true of the transition metals. They just have a couple more options. And this region just here of our non-metals, this is where we end up a situation where we have a enough electronegativity that they can accept electrons, but they also have a low enough electronegativity so they can give it away. And so we have some multiple different types of bonding that can occur. All right, let's just clear off these drawings. So there are two main types of bonding that you need to be aware of. Covalent bonding, which is when you have valence electrons that are shared between atoms. Now, there are two types of covalent bonds. There are non-polar bonds. All right, and if you think of, just remember, when we think of a covalent bond, it's the two electrons being held together between the atoms. All right, a non-polar bond is where there's equal sharing. Okay, all right, and that happens when you have a difference in electronegativity of less than 0.5 between the two atoms. All right, when you have a polar bond, that's when you have a difference in electronegativity on the Pauling scale of greater than 0.5 to 1.7, all right, between the two atoms. And what that means is that one of those atoms is pulling those electrons towards it, all right? So there's not equal sharing. And that results in one of those atoms having a slightly more positive charge in comparison to the other atom, which has a slightly more negative charge. And so the one which has the electrons pulled closer towards it, slightly more negative. The one which has the electron pair pulled away from it, slightly more positive. All right, our other main type of bonding to be mindful of is ionic bonding. Okay, and this is where we have electrons being transferred from one atom to another, okay, when we have the formation of compounds. All right, and this happens when there is significantly large differences in electronegativity, all right, such as a difference of 1.7 or higher. All right, and what's happening here is our valence electrons from our material that is giving away its electron, okay, our cation, all right, by giving away the cation, it goes back to the prior shell of electrons, and since that's now full, it's a more stable arrangement. Now, our material that is accepting the electron, our anion, by accepting the electron, it is getting closer to have a full shell of electrons, and that enables it to actually be more stable. All right, and that's what's driving that. All right, same deal with the covalent bonds. All right, by sharing their electrons, they are closer to having a full outer shell of electrons, so a full valence shell of electrons, and that means that they are more stable. All right, now there is a third type of bonding that is worth mentioning, okay, and that is metallic bonding. All right, and just to be honest, there are other types of bonding beyond these three, but they're not a HSC level thing to worry about. All right, and in the case of metallic bonds, this is a bit of an unusual situation that typically occurs with metals in their elemental form. All right, okay, and that is where the valence electrons are not held onto closely by the atoms of the metal. And this results in a sea of surrounding electrons that are considered to be delocalized. All right, and in that case, these valence electrons surrounding the positive nucleus of the atom and the core electrons, which, while negative, the particle itself is a net positive because you have more protons. All right, that you have that sitting there surrounded by the valence electrons. They don't really belong to any one atom. Okay, and that's what actually makes metals be electrically conductive and able to conduct heat, all right, because those valence electrons can actually move and transfer energy. So, three types of bonding, people. Three types of bonding. All right, we have metallic bonding. All right, now the type of bonding informs the properties of the substance. Metals, materials with metallic bonds, they typically are solid at room temperature. They have a crystalline structure. The one exception of that is mercury, which I'm going to get you to do some further reading on why it is a liquid. All right, we have usually a high melting point in the case of metals. All right, and they have good heat and electrical conductivity. All right, and they're usually soft enough to be bent and squished and worked with, so they're malleable and ductile, and in most cases, if they're polished, they will be shiny and have a lustrous surface. Okay, when we're talking about ionic materials, all right, in most cases, just like metals, all right, you have a network solid, okay? But in the case of an ionic material, it is a network solid made up of positive and negative cations and anions. Okay, now they're held together by an electrostatic force, all right, that forms a repeating network of crystals. Okay, now in this case here, when we say the formula of an ionic compound, all right, the formula is indicative of the ratio of cations to anions in their simplest possible ratio. Okay, but the material itself is a network. All right. Now, in general, their properties from a ionic bond, they are in general crystalline at room temperature. They usually have a very high melting point. If the electrostatic bond that is holding the cations and anions together is weaker than the thermal energy of water, then the hydrogen bonding of water is able to actually dissolve the ionic material. all right, and actually break it down to individual cations and anions that are surrounded by water, and it can be dissolved. We'll look at that later in Module 2. All right. When they're a solid, because all their cations and anions are in a fixed position, ionic solids cannot conduct electricity. However, when they are molten or they are dissolved in water, right, i.e. aqueous, they, because those anions and cations can move, they can conduct electricity. And now in general, also, because they are a highly crystalline ordered structure, they can be brittle. Okay, now for covalent bonding, we have two different types of covalent bonds that exist in materials. All right, there's what's known as covalent molecular materials. Okay, and these are what are called discrete particles. So if you think of water, you've got H2O. Each particle of water has just 2 hydrogens and 1 oxygen. All right, so by discrete, we mean single whole number of atoms within a particle. All right, same deal as with mathematics when we say discrete numbers. If we say a discrete number, we're meaning 1, 2, 3, 4. All right, we don't mean 3.5. That's not a discrete number. All right, so discrete particles means we have particles made up of a fixed number of atoms. Okay, that's what a covalent molecular substance is. All right, and the way in which those particles interact with each other and other materials gives that material its observable properties. All right, and in that case, the compound formula is indicative of the entire particle. Okay, if it is a molecular formula. Now, covalent molecular substances, they are usually a gas, liquid, or solid at room temperature, with many of them being gases or liquids. All right, they usually have a low melting point, because if they're a solid, all right, the individual particles are usually not held together by very strong forces. So heating them up will cause them to go into the liquid or the gas state. All right, now usually they do not dissolve in water. All right, and again, because they are fixed particles that don't have positive charge or negative charge that can move around, they typically do not conduct electricity, all right, even when they're melted or dissolved in water. In the case of covalent network materials, all right, we're talking about materials like silicon dioxide, so sand. All right, this happens when you have the sharing of electrons between 2 non-metal atoms, and you have the formation of continuous chains of material, and you end up with this massive network structure that's not dissimilar to a metal or a or an ionic substance. All right, but because they have covalent bonds, all right, the bonding is through sharing of electrons between those atoms, and their properties end up a little bit different. Okay, they're ultimately determined by the structure of the network. All right, and unlike covalent molecular, the formula in the case of a network solid is again indicative of the simplest ratio of elements across that network, just like an ionic compound or a salt. All right, now most covalent networks, all right, they are solid at room temperature. They have very high melting points usually. They typically don't dissolve in water because they're a large network solid. All right, and because all of their particles are fixed in position, they typically don't conduct electricity. And if they are melted or dissolved in water, all right, they usually still don't conduct electricity. All right, so I've got more information about what I've been talking about in the lesson notes. If you go to page 61, you'll find those. You'll also find a brief little note on how each of the models that for the different types of bonding, which is pictured at the bottom of this table, how each of them has some issues. And so the thing to remember with a model in science, it's a metaphor to explain how something works. All right, it's only going to work in specific cases. All right. Okay, and so we need to understand the limitations of the model. So I suggest at the end of this video, you go and read page 61 of the notes and get an understanding of how metallic, ionic, and covalent bonding actually has some limitation as a model to explain the different types of bonding that is going on in substances. All right, and that'll wrap us up for today. All right, let's get on with the lesson, people. Bye.